And I think for this exam, we'll definitely want a calculator handy. It will make things go a lot faster. So make sure you bring a calculator that's not attached to your phone to the exam. So we're going to keep incrementing 30, see if it's divisible by 3. It is. See if 30 is divisible by 4. You could also shortcut a lot of this with mental math if you feel comfortable. Is 30 divisible by 5? It is. Now, last thing we checked was 5. So do you see the next one that we check is 6? But that starts us repeating the pattern because we already have 6 written down. That's when you know you can stop and you found all of them. So these are all the factors of 30. Now, how do we find the prime factors? That's when we did our factor tree, and we would also reference our list of prime numbers so that we know what is a prime number. So why don't we all get started on our factor tree? Remember, everybody's middle part of the tree might look different, but we're all going to get to the same bottom of the branches, the same prime numbers at the end. So we keep dividing until at the end there are only prime numbers left. So 240 could be expressed as 2 occurs 1, 2, 3, 4. So that'd be 2 to the 4th. 3 occurs once, and 5 occurs once. The good thing about this section is we could always check our work. 2 times 2 times 2 times 2 is 2 to the 4th, times 3, times 5, and we get back to where we expected. Any questions about the prime factorization? If not, we'll go on. Now, if y'all remember in 5.1, there was a list of divisibility rules. Don't worry about writing that down on your formula sheet. I'll include that table as part of the quiz as like an image before that subsequent problem. Now, I don't happen to have it with me now. Let me grab it. One second, I'll bring it on the screen. Okay, so here's our divisibility rules chart that would be provided on the exam. Take a moment to identify which of these divisibility rules applies to tell us that 736 is divisible by 4, and you'll select the correct box. So let's go at 4. Doesn't it say it's divisible by 4 if the last 2 digits are divisible by 4? So we'd look which one of these says that. That would be the correct answer choice. Now, if we were to ask what makes it divisible by 2, it would be this one, right? So we know how to work these kind of problems. Oh, do we see here I did the prime factorization even though it just asked for all the prime factors for our previous problem? So sorry about that. It still helps you find all the prime factors, but we would just say 2, 3, and 5 are the prime factors. And it'd probably be a list that you're check marking. So any prime number that divides into it. We've already practiced prime factorization, but here we're asked for the prime factorization of 460. If y'all are comfortable with this, since we already did an example, maybe we'd go to the greatest common factor just to make sure we've got time for everything. Because greatest common factor includes prime factorization. Why don't we all take a minute to attempt this on our own? When finding greatest common factor or least common multiple, you always want to write the prime factorization of both, preferably next to each other so you can easily reference what they have in common. And this is probably one of the things that you want to write down just as a helpful reminder, because with greatest common factor, the way we do about this is you only choose the prime numbers that are common to both expressions. So we look, there's a 3 and a 5 for the first one, a 2 and a 5 for the second one. The only prime that's common to both is the 5 itself. Once you know you're going to keep the 5, the next thing you have to remember for greatest common factor is, even though it says greatest common factor, for those common primes, you choose the least possible exponent that appears. Now, in both of these cases, they're both squared, so we're not going to really have to make a choice, but if they're ever different, you choose the least one for greatest common factor. So that'd be 5 squared. It might be represented that way, or we might have to multiply that out and get 25. So greatest common factor, choose all the common primes and pick the least exponent possible for each of those common primes. Multiply it together, that's the greatest common factor. Now, least common multiple is a similar setup. You still do prime factorization first, so I'll give everybody a second to do that. And I think I saw some people doing this. This could be a great time to at least start your note sheet, right? As you hear or see things that you want to include, it might be a good use of time as we're working through these problems. So in this case, would we agree with these prime factorizations? Okay, great. So for least common multiple, we want to remember this one. Least common multiple wants all the prime factors, even if they're not common. So we see there's a 2, a 5, and a 7. So the least common multiple is going to have a 2, a 5, and a 7. Now we just have to determine what's the exponent that goes on each of these. Least common multiple, even though it's the least, wants the greatest exponent possible. So for the 2, there's only one 2, and it's squared, so this would be squared. Now there's two 5s, but do we agree they're both to the same first exponent? But if they differed, we would choose the highest. So 5 to the first, we can just leave it like that. 7 is by itself, 7 to the first. So the least common multiple is this, and if we multiply that out, we would get 140. Great, and that's the end of 5.1 material, or our review of 5.1. Does anybody need more time here, or are we good to go to 5.2?
I have a question.
Yeah, Tiffany.
The least common multiple that always needs to be completely added, or I mean, not added, you know, I mean figured.
Do you mean like multiplied?
Yes, exactly.
So Tiffany, that's a good question. It's all going to depend on how the question's phrased. Y'all might have seen some where it's multiple choice, right? And if it's multiple choice, you'd probably select this one. But sometimes I ask you to type your answer in the blank. So if there's like a box that you're going to type in your answer, that's when you'd want to figure it and multiply it. So you can type this is the value. But the only way you get to this value is by making this first. So this always happens as part of the problem solving process. And depending on how the problem comes up on the exam, either you're going to select this from a list of options, or if there's a box, you're going to multiply them together so that you can type in that numerical value.
Okay, thank you.
Thank you. Okay, I saw a question. If one of the 5s was to the square, so let's pretend that this is not the case here, but let's pretend this one was 5 squared. In this case, since the least common multiple wants the greatest exponent possible, then the 5 in our least common multiple would also be squared. But had this been greatest common factor, that's when you choose the least exponent. So if this was greatest common factor, I'll do that here, of these, first it would only choose the common prime, which is 5, and it would choose the least exponent possible, which is 5 to the first. Okay. So, but this wasn't really squared, so I'm going to erase that and erase that so there's no confusion on that problem. Kimberly, does that kind of clarify the question? Okay, great, thank you. And Tiffany, did that clarify your question as well?
Yes, ma'am.
Okay, perfect. So now, unless there's other questions about 5.1, which we're happy to answer, if not, let's turn our attention to some 5.2. 5.2 is when we talked about the idea of these kind of, you've got the whole real numbers, But if you want, you could subcategorize them into smaller and smaller sections. So we describe things like the natural numbers. Let me see if I can find that on the notes. So we talked about things like the natural numbers, which were starting at 1 and increasing through those next integers. The whole numbers differed by just adding in 0. The integers, all the positive and negative integers. So keeping those groups in mind, remember natural numbers are only the positive integers. Whole numbers are the positive integers plus 0. Integers are just what we'd expect. So let's ask ourselves, is it true or false that every integer is positive? Why don't you type it in the chat? What do we think? T or F? Thanks, Kimberly. That's exactly correct. Correct, Tiffany? Great. So we're getting some input that that would be false. That's correct because -1 is an integer, right? And it's definitely not positive. Now, is every whole number guaranteed to be a natural number? So you're starting with the whole numbers, not just one of them, but every whole number. Is every whole number fitting the idea of natural number? And I'll write out the whole numbers for us and the natural numbers. Once you think you have an answer, type it in the chat. Okay, Tiffany, that's correct. Exactly right, that's the right reasoning, Tiffany. Ashley, correct. Kimberly, correct. Great work. I'm getting all false, which is exactly right, because do you see the only issue comes from the 0. 0 is the only one that this fails for, but since they said every, if it fails once, it's false. So great work, everybody. That would be false. Now we get into our inequalities. Remember how you read the inequality? The smaller part of the angle, I like to think of as supposed to be pointing towards the smaller number. The bigger part of the angle is supposed to be pointing towards the bigger number. At least that's how it's supposed to work. Now, especially when we're given an inequality that looks rather complex on the left side, do we agree it would benefit us to simplify the complicated stuff first and then compare if the inequality is true or false? So minus a -4, minus a negative would become a positive, right? So the left side is equivalent to 4. So now we judge this. Is this true? Remember, bigger side of the inequality going to the bigger number. So this is saying 4 is bigger than 2. True statement, right? So we would say this is true. Okay, I'll give everybody a moment to look at our next one. Type your idea in the chat. Okay, correct Tiffany, correct Ashley, correct Kelly, perfect Latifa. Great job, everyone. So you are saying false because this is saying 2 is less than or equal to -3. That's definitely not true. We're also going to get practice evaluating absolute values. Remember, if you see straight line, something, straight line, that's absolute value. All absolute value does is it makes whatever's on the inside after you simplify the inside first, then you just make whatever's on the inside positive. So what's inside this absolute value is 7. 7's already positive, so it doesn't change anything. But in this case, what's on the inside of the absolute value is -7. Absolute value makes it the positive version, so this would be also 7. Now, our next example combines absolute value, but also order of operations. Do we agree this negative is separate from the absolute value symbol? So we would first need to evaluate this absolute value. Once this is simplified inside the box, then you apply the negative. So why don't you all take a moment to evaluate that? Perfect, Tiffany, that's exactly right. Well done. Perfect, Ashley, perfect, Kimberly. You guys are doing great. That's -7. Because it would be 7 from the first absolute value. Notice I'm now in parentheses, no longer absolute value, distribute the negative, -7. Now this next example is a case where we've got to do a bit more to simplify the inside before we apply the absolute value. Okay. Great job, everybody. So that would be, we'd simplify, leave the absolute values alone. 7 plus -3 is 4. Absolute value of 4 is still itself 4. Calculate this next one and try to think about why it would be a different value. Describe it to yourself. Now the first one is absolute value of 7, which is just 7, plus absolute value of -3 is 3. So since it made both of them positive before we added it, we would get the overall value of 10. Identify if this is true or false. Remember, when it looks complicated, simplify each side first before you evaluate whether it's true or false. Correct, Tiffany, from your previous problem that you sent in the chat. Correct, Tiffany. Correct, Kimberly. So when we evaluate this one, 7 minus 5 is 2. Absolute value of 2 is 2. This is saying 2 is greater than -15. That's a true statement. Now we evaluate these with exponents, and we want to be careful with the signs. So why don't we all take a moment to evaluate each of these 4. We'll discuss around 713. Does anybody need more time for these problems? Okay, so for the first one, did y'all get 64 positive, -64, And then next we would have a negative 64, positive 64. And one thing to keep in mind is once you know the first two, do we see this is just part of this, except they additionally added a negative in front? So it's kind of like once you know the first one is positive 64, then you see it's just adding a negative in front, which makes it negative 64. Same with that one. To look through the patterns. Next comes order of operations. Remember parentheses, exponents, multiply or divide, add and subtract. So take a moment to simplify this. I did make it up. It might not be an integer. It might be a fraction, finally. Oh, 1 second. Let's see. Oh, it's definitely 16. Sorry about that. I was trying to do it in my head. I think 2 to the 6 is 64, right? So these should be variations of 16 and positive 16. I do apologize about that. Positive 16, negative 16, negative 16, and positive 16. So hopefully that clears things up. Y'all were right. It was a 16. And thank you, Kimberly, for pointing that out. And Latifa, whenever you're done with this page, if you would let me know in the chat, but no rush. Okay, great. Thank you. It's good that we came back and corrected that as well. Okay, so our next one is this order of operations. Now, as we simplify these, I like to simplify them piece at a time before I put them in my calculator. 2 minus 5 is negative 3. And while I'm at it, I might multiply exponents next. So 4 squared is 16. Divide that by 9 minus 2 squared is 4. So we're just doing these progressive simplifications. 5 times negative 3 would be negative 15 minus 16 all over 9 minus 4 is 5. I'm going to simplify the top. The top would be negative 31 over 5. So that would be our answer. Any questions about the order of operations for this problem? Okay, good work, everyone. Why don't y'all take a moment to attempt the next one? Parentheses, then exponents, multiply or divide, add or subtract. Kelly, that's exactly right. Well done. Yeah, if you get an answer, send it in the chat. Perfect, Ashley. Well done. Perfect, Kimberly. Great job, Tiffany. That's exactly right. Perfect, Athos. Great, so as we work through this one, we keep in mind parentheses. So I'm going to deal with these parentheses first. That would be a -4. Next, I'm going to deal with exponents. 6 squared is 36. That's getting multiplied by the -4. Plus, I could deal with this multiplication of 20. Now 36 times -4 would be -144. That we're then adding 22, so we would get -124. Good work, everyone. So now we're on to 5.3. And one thing that y'all remember in the 5.3, right, it had the formatting where it was like, I can't type a fraction, so the first box is the numerator divided by, and then the second box was the denominator. Expect similar formatting for the exam. So here we're asked to reduce 15 divided by 25 to lowest terms. So we know in our exam, it would look like something like first box, second box, and we type in the numbers. Give everybody time on that. And remember, if y'all have questions that y'all'd like to ask, definitely ask them in voice or in the chat. This is time for y'all's review. Perfect, Kimberly. Excellent, Caitlin. Perfect, Tiffany. So we know there's lots of ways to find the lowest term. One of the ways is to write the prime factorization of both, right? And then cancel out any common terms. That's particularly helpful when it's a bigger fraction with bigger numbers. But with one like this, we might be able to quickly see, oh, 3 times 5 is 15. 5 times 5 is 25. This is actually its prime factorization. Cancel the things that are the same above and below. And that would leave us with 3 divided by 5. And one thing to watch in this section, sometimes the answers say, write your answer in lowest terms. So if that's the case for a problem later on, make sure that that's followed. Now also in this section, we had the idea of mixed numbers and improper fractions. Mixed numbers were these numbers where we had some integer paired with some fraction. And we know there's an implied addition here. We just don't write it because of space. This is really 3 plus 6/8. Now improper fractions are fractions where the top number is bigger than the bottom number. Let's go over the procedure to find the improper fraction together. We would start with what we're given, 3/6/8. And this is equal to, first, the denominator of the fraction is the exact same for the improper fraction. So I'm going to copy over 8 immediately. That's always the case. And then what you would do otherwise is we would take the integer 3, multiply it by the 8 in our calculator. So take the integer times the denominator. Whatever that number is, you then have to add the top number to it. So plus 6. And we would get 30/8. So the way I did that is I took the integer times the denominator, gave us 24, and then you add the top of the fraction. And that's what goes in the top part there. Would you like me to write an additional one to practice on your own for this type? Okay, I'll do one. So same instructions if you'd like to work on this one. Write that as an improper fraction. Correct, Tiffany. That was the exact right answer for the previous problem. Okay, so we know the denominator stays the same. And then to find the next piece, you take 4 times the bottom. So 4 times 9 is 36. You add 7 to that. So I believe we would get 43 over 9. Great. So we've gone from mixed number to improper fraction, but we can also go from improper fraction to mixed number. And that's what we do in our next example. We'll go through one together, and then I'll give you one to work on your own similar to before. So what happens first is we know that it's going to be some number with some fraction attached to it. And just as before, the denominator of the original is the denominator of the fraction part of the mixed number. So we're just going to copy down 5. But we need to figure out what is the integer part, which is how much does 5 go perfectly into 36, and then what's the remaining decimal part, which is the fraction. So we would first take our 36, the number at top, and divide it by 5 in our calculator. What we're looking for here is that integer part. Do we see that's a 7? So 7 is what goes here. And then we need to ask ourselves, well, just how close does 7 times 35 get us to 36, the number in question? So 7 times 5, multiplying these together, gives us 35. So how close were we to 36? 1 away, so 1 goes in the blank. So exactly right, Tiffany and Kimberly, well done. For practice, why don't we convert this into a mixed number? Perfect, Kimberly. Excellent, Tiffany. Excellent, Athos. So on this one, we would take our 63, divide it by 8. That tells us it goes in 7 times perfectly. We know the denominator of the fraction is 8, so 7 times 8 would get us to 56, but we wanted to get to 63. 63 minus 56 is 7. So it's equivalent to 7 and 7/8. Now we also learned or reviewed how to multiply, add, subtract, and divide fractions. We know for multiplying fractions, it's top times top and bottom times bottom. And notice this is the case where they said reduce to lowest terms. So whatever our answer is, we'd want to reduce to lowest terms before we type it in. 4 times 6, 24. 5 times 11 is 55. So then we would have to think, is there anything common that we could cancel out for these? If we write the prime factorizations of both, I believe we would get 24 is 2 times 2 times 2 times 3. And 55 is 5 times 11. Do we see there's nothing common? So it's already in lowest terms, so we would just type that in. Now for dividing fractions, our phrase that we want to keep in mind is keep the first fraction, change the sign to multiplication, and then flip the second fraction. So keep it, change it, flip it. So why don't y'all work on this, and when you find it, reduce your answer to lowest terms.
So would the last answer be the 24 over 55? Because you couldn't reduce it down anymore?
That's exactly right, Tiffany.
Thank you.
So we would keep the first fraction, change the sign, flip the second fraction, and then it's fraction multiplication, top times top, bottom times bottom. And I got 16 over 12. Definitely looks like there's a lot of maybe cancellation that could occur here. So we're going to write out their prime factorizations. If we need to sketch off to the side, we do so. And we notice that 2 pairs of 2's from the top and the bottom would cancel, leaving us with just 4/3. So we would type 4/3 as our final answer. And we know 16 over 12 is equivalent to 4/3. Just writing it in lowest terms, since there's so many different ways to write this value, it's good for us all to agree upon one to write. That's kind of the idea. Are there any questions from this example? Okay. Now we know adding and multiplying fractions tends to be faster. No, sorry. Multiplying and dividing fractions tends to be faster than adding or subtracting fractions. The key idea with adding and subtracting fractions is that you can only add and subtract fractions that have the same denominator. So first you have to get a same denominator, but we can't change the value of the expression. So we do what's called the fancy one, right? You think about what you want to be there, and you write that times the thing that you want to be there, but you also have to put that at the top. So whenever we work through these problems, we always write it out, giving ourselves a bit of space off to the side, because we're going to start to multiply by something. What would be the least common denominator between a 4 and a 5?
20?
Perfect, Tiffany, exactly right, 20. So 4 times what would give you that 20 that we want?
5.
Perfect. But if I just write the 5 below, I've changed the problem. So we also are forced to write a 5 above, because we know this is really 1, and multiplying by 1 doesn't change anything. For similar reasons, we would get 5 times 4 is 20. That was our goal. But if it's here, it also has to be here. Top times top, bottom times bottom, we would get 5/20ths plus top times top, bottom times bottom, 8/20ths. Since these are the same now in the bottom, we can add it. And when you add fractions, you keep the bottom the same, and then you just add the top. So we would have 5 plus 8 is, I believe, 13, which is already in lowest terms, 13 over 20. How do we know that? 13 is a prime number, so it's always in lowest terms with whatever it's paired with, apart from itself. So why don't y'all work on the next one on your own? And when you get your answer reduced to lowest terms, type it in the chat. Caitlin, I don't think so either. Kimberly, that's correct. I think, Caitlin, look at your denominator. Okay, good. Okay, Athos, that's the correct value in Tiffany as well, but I think we could get it to a lowest terms. So you have the right value, just get it to lowest terms next. Do we agree in this case, the least common denominator I could probably get is 35 times 6, right? So I'm going to take 2 over 6 and multiply it by 5 over 5 minus 3/5 and multiply it by 6 over 6. Top times top would be 10, bottom times bottom is 30. So the first fraction becomes 10/30ths in its equivalent form minus 18/30ths. So we get negative 8 over 30, which is the correct value. But since it said lowest terms, specifically, do we see that I could write negative 8 as negative 2 times 4 and 30 as 2 times 15? So those common 2's cancel, but there's nothing else similar between 4 and 15, so it is then in lowest terms. So it would just be negative 4 over 15. Exactly right, Tiffany. So that's it for 5.3. Remember, 5.4 was not covered, so it won't be on this test or the final, it's just not covered for our class. And then we can move to 5.5. Before we do so, is there anything that y'all wanted to review further from 5.3? Okay, so if not, let's go to 5.5. Now here, just because there's a lot of writing, I just copied some from our 5.5 quiz. I thought we could answer these true or false. Why don't y'all take a moment to evaluate question 14, 15, and 16. Answer whether they're true or false. Remember, rational numbers is the set of all fractions where you can do one integer divided by another integer. Specifically from this section, this is where we talked about how each of these descriptions of real numbers can be categorized and found in subsets, right? So you can refer to the 5.5 notes and it describes each of these like name categories. Kimberly, correct? So for these problems, it would be helpful in our note sheets to have the descriptions of these written out. So like natural numbers is this thing, right? Integers is all of the positive and negative and equal to 0 ones. We know that dot, dot, dot means pattern continues. And then rational numbers are the fractions of integers. any fraction that you can form of integers is a rational number. So from this, I think we could say every natural number is positive. Looking at the list of natural numbers, that's true. But if that's true, do we see the next one is definitely false? Every natural number is negative. That's false. They're actually all positive. Now, the next one is something that we talked about. Every integer is a rational number. That's saying start with the integer, like maybe 5. Could I write this as a rational number? Definitely so, right? I could write it as 5 over 1 in its most basic lowest form, or lowest terms. But I could also write it as 10 over 2. There's many different ways to write 5 as a fraction of integers, so that's true. But is the reverse true? What if it said every rational number is guaranteed to be an integer? Is that true or false? That would be false, right? Because what about the example of 1/2? Definitely a rational number, but not an integer. So the order of this implication is important. Oh, which was our next question. Every rational number is integer. That would be false. So if we have the description of these sets of numbers in front of us, then we can evaluate these true and false statements. Now, here we're asked to enter a number that is between 4.6 and 5.7, but not just any number. Do we see it says enter an integer? So integers are those like everything that's -3, -4, -5, continuing on, all the way up to 0, 1, 2, 3, 4, 5, continuing on and on. The only integer that's between these two is 5. So we just enter 5 in the blank. Now here, enter a whole number that's greater than 13 and less than or equal to 20. What would happen if I put in 14.5? It's between 13 and 20. Why is that still incorrect reasoning, even though it is between 13 and 20? Perfect, it's not a whole number. Getting very good at reading lips from this class. Y'all have given me a fringe benefit. So it's not a whole number, but 14 would work. And this would be one of those problems where I would have made the rubric where, for instance, could I include 13 if it said greater than 13? No, good. So 13 wouldn't count, but 14 would be the first one. Oh, let's fix that. Okay, so 14 is the first one that we could type in. I could type in 15, I could type in 16, 17, 18, 19. Now we need to be cautious. Less than or equal to 20, is 20 okay? Yes, because it's or equal to. So of course, don't type all of these, but if people typed any of these, they would get full credit for this problem. Now in our notes, let me show us that section. This was back weeks ago because we did have that 2-week difference from the storm. So weeks ago, we did talk about this idea of certain properties that work with our real numbers. They work so well that we just probably have never thought about them before, but we illustrated some situations where they don't work just to point out that these are important things to have. So remember, the closure property was that if you start in a group and you do some operation with another thing in the group, you stay in the group. So that was like saying integer plus integer stays integer. Commutative was that you could reverse the order of the operation and it doesn't change the value. Associative was you could regroup things. So like A plus B and then plus C is the same as A plus B first, or sorry, B plus C first and then plus A, similar for multiplication. Now, identity was the idea that there should be some element in your number system that if you add that number to any other number, you stay at the number. For us, that's 0. Similar for multiplication, anything times 1 stays the thing that it is. Inverse tells us we should be able to get back to the identity. So if I'm like at 7, I could add -7 and get back to 0. Or if I'm at 7, I should be able to multiply by 1/7 to get back to the multiplicative identity 1. And finally, we had distributive property. If you're mixing the operations A times B plus C, we could think of the idea of distributing. That's the same as AB plus BC. So for our next one, look at the statement written here. And based on those that we just described, identify which of these properties it's illustrating. So I think what's happening here is, notice we start with 2 times 3. And it says it's equal to 3 times 2. What has occurred to make the left side visually different looking than the right side? Not different in value, but different in expression. We've kind of reversed the order, right? That's the idea of the commutative property. 2 times 3 should be the same as 3 times 2, right? You can switch the order of the operation. So this illustrates the commutative property. Another example of the commutative property that I could have written out, this is for multiplication, but for addition, couldn't I have said 2 plus 3 is the same as 3 plus 2? Okay. Let's look at the next one, and I'll write out a few more if we'd like to practice this. Think about which property this illustrates. 5 plus negative 5 would be equal to 0. And for this one, as you make your note sheet, it might be nice to have like the names and then like one example written next to it that illustrates that. I think would be an efficient use of space. Correct, Tiffany? Exactly right. So here, the structure that I'm seeing is we're starting at 5 and we're adding something and we get to 0. Now, we're particularly interested if we're equal to 0 or 1 because 0 and 1 are the identities, right? So this is saying you can start somewhere, add something to it, and get back to the identity. Now, this is not the identity property, right? Because the identity property says you stay put. But instead, it's the inverse property to show that you can get back to the identity. So this would be the inverse property. Now, we've only done 2 of these. Are there any other properties that y'all would like to see examples of and guess? I could write some more on the screen. If so, send the name of it in the chat. Okay, great. At those, I'll include that. Are there any more before I start writing an example? Okay. Somebody send in one thing other than associative, because if people know I'm writing the associative, that gives the game away. So let's do 2. One will be an example of one will be an example of the other. Okay, good. So I got associative enclosure. So y'all don't know which one I'm writing first. Oh, sorry, I'm losing my screen. Okay. Think about which property this tells us. 2 plus 4 equals an even integer. Correct, Kimberly. How can we describe 2 and 4? They are also even integers, right? So this is saying like even integer plus even integer stays an even integer. That's the idea of closure. You have something, you do something to it and something else in the group, you stay in the group. So that would be our closure property. Now let's go through another example. I'm going to write a multiplicative version and an additive version. Both of these are illustrating the same property. One is in addition, one is in multiplication. Correct, Kimberly? Well done. Here, do we see the order's not changing? It's not like I'm flipping the direction, but what I'm doing is I'm shifting the parentheses, and parentheses tell you what to do first. Do we agree first it was saying 3 times 5? And then times 2? But what this is saying is that's equal to 2 times 3 first, and then times 5. It's telling you the order that you multiply the pairs doesn't matter. Same with addition. First we were adding 3 and 5 and then adding 2, but that's the same as taking 2 and 3 and then adding 5. So this would be an example of associative. And I think there's some more of these on your quiz from this section if you wanted to review. Has anybody gone back into the quizzes after they're due? Are you able to get into the quizzes after the due date? Yes, no. Maybe if somebody could check, I want to make sure they're still accessible. Okay. So that was it for 5-5. We'll start 5-6, and it was exponents. I'll give everybody a moment to work on the 3 that they see on the screen. We'll start talking about this maybe about 7:55. Okay, thank you, Kimberly, for telling me they're locked. I will try to fix that. Oh, Latifa, you can get in? Oh, that's good to know. Perfect. Kimberly, were you trying 5.7 or were you trying a previous one? Because 5.7 doesn't open till 9. Athos, you can get into? Okay, great. Kimberly, could you try like the 5.11? Thank y'all for the additional feedback. So if you can't get in, I think that'd be a good review tool to just go through those problems, cover up the answer, and then check your work. Okay, let's look at that after class. Thanks for letting me know, Kimberly. If anybody else tries to later and can't get in, just send me a Canvas message and we'll do that case by case. So with exponents, the key thing is if they have the same base, which is what we're raising the exponent to, then if you multiply the same base with one exponent times the same base to a different exponent, what happens is the exponents can combine and add. So we could write this as 3 to the 5th is what it's equal to. Now, particularly with our Canvas quizzes, one of the ways that we saw this being answered is I had already described the 3 exponent, so that all we had to type in the box was the 5. So there might be a similar formatting for the exam as well. Now what happens is whenever you have an exponent, 3 squared, raised to another exponent, in that case, the exponents multiply. 2 times 3 is 6. So this would be 3 to the 6. And if we're trying to fit the exam formatting, because we can't type in that kind of formula into Canvas, it would be like 3, exponent button, and then there would be your box. we type in 6. Okay, why don't y'all work on the next two? You remember when same base is being divided, you would subtract the exponents, top exponent minus bottom exponent. So we get 3 to the negative 1, or in our quiz formatting, we type in -1 to the box. Now the other thing that we want to remember is if we ever have some number to a negative exponent, you could rewrite that as 1 over that same number to the positive version. So negative exponent, send it to the bottom of the fraction where you change the exponent to now be positive. So if we see 2 to the -6, that would be the same as 1 over 2 to the 6th. And to fit into our Canvas formatting, we could see that as 1 divided by 2 to the exponent. Do you see all of this has been included except we just type in the 6th? But this would be how you'd write it if we had paper test, 1 over 2 to the 6th. So any questions from these properties of exponents that we could go over more? So if not, another thing that we learned is anything to the 0 is 1. So even 123 to the 0 is still the value 1. Next up was scientific notation, which was written as some kind of decimal, and then this x representing multiplication, always the x, sum 10 to some number. And based on whether the number is positive or negative, we treat it different. To write it as a decimal, you would find the decimal place in the scientific notation. So 2.36. And since it says 10 cubed, you would take that decimal place, since it's positive, and go to the right 3 places. So 1, 2, 3. So I make my decimal point there. And if we ever have to go over farther than what we have numbers, we put zeros in that place. So this actually is representing 2,360. And if it's to a negative exponent, we just go to the negative direction. So, or to the left, 2.36, now 10 to the -4. You would write out the number. And since it's negative, we would go to the left 4 places. So 1, 2, 3, running out of space. 4. Fill in a 0 anywhere there wasn't a number. So we get 0.000236. Now, if you took this quiz early, there was an error, and I appreciate those of you who alerted me to it. Canvas would just think this is 0, because this is practically 0, right? It would be a very exact measurement. So I made future ones into multiple choice. So for rewriting scientific notation to a negative value, it would be a multiple choice where you select the correct decimal answer so that we can write it exactly. So how do we feel about going from scientific notation to decimals? Good. Okay, let's do the reverse. We can now take decimals to scientific notation. In this case, if there's not a decimal written, it's always to the right of the last digit, right? And then we want to move that decimal place until we get a single number in front of it. Like this had 2 point. The decimal was right after the first digit. So if we're having to go here, do you see we're making it smaller? This is the idea of, or sorry, no, never mind. 1, 2, 3, 4, 5. So this would be 1.24 We had to move it 5 places, but here we have to decide should the 5 be positive or negative. And this is where I misspoke for a second. We moved it 5 to the left, which is true, but if you wanted to undo it, would you need to move it back to the right, which would be a positive 5, or would you need to move it farther to the left? We'd want to move it to the right, right? To undo this. We'd want to be able to go 1, 2, 3, 4, 5. So that's why we're raising it to the positive 5. So basically, if it's a big number, it's going to be to a positive value in scientific notation. If it's a small number, close to 0, it's going to have a negative in scientific notation. Now, I know that might be a little confusing because here, didn't we move to the left and it was negative? But that's because we were reversing the order. It's not going the same direction. In this case, we're taking a decimal and we're saying in order to get into scientific notation, we're having to take away decimal places because it's such a big number. So that's why it would be to the positive 5. Take a moment to find the next one on your own. Tiffany, almost perfect, but I think it would be your exponent. I think it would be the opposite exponent. Kimberly, that's correct. So in this case, do we agree this number, we're starting off very small, very close to 0? So we can, if it helps us mentally remember that this is going to be 10 to some negative number. If it's already really small, it's going to be negative. How many places do we have to move? 1, 2, 3. And that would give us 2.56 times 10. We move 3 places, but we're such a small number, we know it's going to be negative because 10 to the negative represents really small numbers, so it's going to be to the negative 3. So if we're representing a really big number in scientific notation, we see it's to a positive amount, right? We do have to find specifically how much, but if we're representing a really small number in scientific notation, it's going to be to the negative. Now, the left and right approach is whenever you're going from scientific notation to decimal, which is the reverse of this. That's where you focus on left and right. So we have 2 different strategies based on what you're starting with. If you're starting with scientific notation to decimal, that's the idea of the left and right moving it. But if you start with a regular number and you get it to scientific notation, that's what we were doing in our last 2 examples. Would you like additional problems related to this? How do we feel about this topic? Okay. Everybody seems good. We also learned how to multiply and divide in scientific notation. And this is the idea where you group like things, this times this times this. If it helps you rewrite it. So we're going to take whatever 2.36 is and multiply that by 1.23. And that's going to be times our 10 to the 5th times 10 to the negative 3. But here we use our properties of exponents because this could be simplified. Since it's the same base, right, and you're multiplying, you would add the exponent. So write the simplified exponent there, multiply these. So in this case, we would add the exponents. So 5 plus negative 3 would be positive 2. So that would be our final answer. So remember, multiply like things, and then use our exponent rules to simplify this to a single exponent. Now the next one is similar. Whenever you're dividing.
I'm sorry. I just have
Yes.
a question. So would we need to figure it all the way out or just leave it like you did with the 2 point?
Oh, like this would be our final answer.
Okay, got
So
it.
you're right. So I guess, and this doesn't have words attached to it. So the word description along with it would be write the answer in scientific notation. And this is scientific notation. So that's why we could leave it like that. It's a good question. If we wanted to expand it out, like what we were doing here, it would say you start with the scientific and then it would say like the instructions write as a decimal. That's kind of what you'd be looking for there. Good question, Tiffany. Now for our next one, we would remember to divide like things. This thing divided by this thing, and that's going to be the new number in front. This divided by this, and then we need to think when you have the same base and you're dividing it, you would subtract their exponents. So what times 10 to the what? So 2.6 divided by 1.3 is 2. And then 10 to the 5th divided by 10 squared, you would subtract those exponents. So 5 minus 2 would be 3. So we'd get 2 times 10 to the 3, or if you want to write it as 2.0, that's great as well. Perfect, Athos, exactly right. Correct, Kimberly, well done. And that finishes up 5.6. So our last material that we have for our class period is 5.7, which would actually be good practice for y'all's 5.7 quiz. Remember, it's technically available till Wednesday at midnight, but the chapter 5 exam is also available till Wednesday at midnight, so you wouldn't want to wait to do the 5.7 quiz, right? Because that's going to hold up your chapter 5. So a little bit of planning there. And I just pretty much took these from the 5.7 quiz I made, and we've changed the numbers. So it's a very good practice for your 5.7 quiz. So here we say, find the first 4 terms of the arithmetic sequence if the first term is 6 and the common difference is D. And just so we're comfortable with this phrasing, do we see that the A sub 1 and then there's a blank? This is where we write in the first term. A sub 2 is the second term. This is where we'd write in the second term. A sub 3 is where we'd write the third term. And the order matters in here because it's this, then this, then this. A sub 4 is the fourth term. So I'll give everybody a minute to find the sequence. I would write it out on my paper and then type them in if it was me. We know it's arithmetic, so it's a common difference. Starts at 6, adds 5 each time. So do y'all agree with 6, 11, 16, and 21? Now, the one thing to keep in mind is we do type 6 in for the first blank, even though they gave us this, it's just kind of a freebie that goes in the first blank because it's the first term. Key phrase was arithmetic, and then they gave us the first term and the common difference. So good job. Now here it says consider the arithmetic sequence. Write the formula that correctly represents the sequence given. If this was the Canvas quiz, there would be a list of formulas and you'd select the correct one. But the best way to do those problems is to write it for yourself and then visually match which one matches your answer. So I'll give everybody a second to write out the arithmetic sequence. The formula you'd want to reference is this. So to write out the formula, you should first identify the first term, and then you should identify the common difference. Those are the only two things along with the formula structure that we would need. Our first term is 2, so that's going to take the place of A1 here, and our formula here. N minus 1, n always stays the variable. But as we evaluate the common difference, we think, how do you get to 6 if you're adding plus 4? Let's verify that holds. 6 plus 10 is also plus 4. 10 plus 4 is also 14. 14 plus 4 is 18. So our common difference matches. We found the right one. So then if there was a list of options, you would just select the one that matches this one. And just to verify, would this be the same thing? Yeah, by our commutative property, right? Because all I've done is I've switched the order that I multiply, but it's the same. And this is probably the more standard way to write it, because we generally write constant multiples at the front of things. So any questions on this type of problem? This is from our new material. Okay. Oh, that's nice. I think that's a compliment. Tell him thank you. Glad he's learning math along with everybody. Tell him he's expected to take the exam as well. So we will continue with our next one. Find the first 4 terms in the keyword geometric sequence. So we know geometrics are constant multiples, right? So this would be a good one to write out the sequence and then carefully write it in the right order in our blanks. So give everybody some time to do that. Oh, I get it. I think it's because of the earbuds. That's what makes it that joke. Because I was thinking my hair is not on the side of my ears. That makes sense. Okay, perfect, Kimberly. That's exactly right. So with this one, always start at the first term and then multiply by 3 would give us 18. Multiply by 3 would give us 54. Multiply by 3 again would give us 162. So we take 6, 18, 54, and 162. That would be our answers there. And keyword geometric, do keep track whether it's asking geometric or arithmetic, because then we would add or multiply. Now we've been given a sequence. Can we find the formula? I'll write down the relevant formula. Definitely make sure these are included in your note sheet. So here the variable n is in the exponent. So we know A1 is first term. For us, that would be 3. So we would have A sub n equals 3 times. Now we have to identify our common ratio. So we look at the pattern. How do you get to here if it's multiplying? Times 2. Let's verify that holds. 6 times 2 is 12. 12 times 2 is 24. 24 times 2 is 48. So we do have a common ratio of 2. So 2 to the n minus 1. And we would just select whichever formula looks like that from the options below. Great. Now, our last few problems from this is if we have what's known to be an arithmetic sequence. They've given us the first term. They've given us the common difference. And they've asked us to find the 16th term. Now, we know a few approaches. You could write out all the first 16 terms in the sequence, but that might be time consuming. It would be better to use the formula. So let's write a formula for this case and then just evaluate it when n equals 16. So I give everybody, let's talk about this till about work on it on your own till about 8:19. Oh yeah, we'll go back. Okay, great, thank you. And if you find an answer, feel free to type it in the chat and I can check it for you. I think that's a little high. Okay, Tiffany, I think yours is also a little high. For arithmetic sequences, the formula we want to reference is this one. First term plus n minus 1 times the common difference. So let's find our formula. We would say a sub n equals the first term plus n minus 1 times the common difference. But we want to find particularly the 16th term. So here 16 takes on the value of n. So everywhere there's n, we remember order of operations, parentheses occur first. So this would simplify to 15 times 2 plus 9. 15 times 2 multiplication comes next. So we'd have 30 plus 9, and we would get 39. Oh, okay, that makes sense. Okay, great, Kimberly. So the key thing here is to make sure we reference the right formula and then just evaluate for the first term, the second term, and plug in our value. I'll leave it here for a few more seconds if we're writing. So when you're done writing, if you'd like to read through and attempt the next one. Think about what formula goes with geometric sequences. So for this last one, once we've identified our first term as 9, we know that goes where the first term goes in the formula. Common ratio is 2, that is being raised to the n minus 1 power. Specifically, we're finding the fifth term. Now, fifth is close enough that we could have just written out the sequence as well. So that could be an option here. But if we want to go the formula route, simplify parentheses first. So 5 minus 1 is 4. So that's the same as 2 to the fourth. Exponents come next before multiplication. 2 to the fourth is 16. So any questions that we could answer from this problem or clarify? Do we feel pretty comfortable with this material so far? Okay, great. So I think this is actually to the last set of questions on our review. Yep. You're given a list of sequence. Write in whether they represent arithmetic or geometric. That is, figure out if they are differing by common difference or by common ratio. And for practice, why don't you also write down that common difference or common ratio along with the labeling. And when you're done, why don't you type in the chat, just type A for arithmetic, G for geometric, and I'll check your work. Correct, Kimberly, and exactly the right differences in ratios. Correct, Caitlin? Correct, Ashley? So in our first one, we're trying to see, is it a constant multiple or a constant adding? And after we look at this, do we agree this is just increasing by 1 each time? So that would be arithmetic with a difference of 1. And in each case, we're not sure whether we're adding constantly or multiplying constantly. You kind of have to think through both and see which one fits. So couldn't we get to from 3 to 6 by adding 3? So then we'd say, okay, what about the next one? If we add 3, we wouldn't get to 12. So that tells us it's not adding. So we go back, okay, how else could we get from 3 to 6? Well, we could multiply by 2. And following that, 3 times 2 is 6. 6 times 2 is 12. Seems to work out. 12 times 2 is 24. So it is geometric, specifically with a ratio of 2. Now for our next one, I definitely don't know a very easy way to multiply 10 and get 8. So let's check arithmetic. It is subtracting 2 each time. But here our difference would be a -2 because we're going down. Now for our final one, we might think, oh, well, 20 minus 10 would get us the first place, but that pattern doesn't hold up, right? So it's not subtracting or adding, but 20 times 0.5 is 10. 10 times 0.5 is 5, so it's multiplying by 0.5, and we would get geometric. So that's kind of our last part, is given sequences, be able to determine which one it fits. And you would just go through and think, could I constantly add something and make this work out? If not, could I constantly multiply by something and make this work out?